Hey everyone, welcome. Today, we're going to head out to the very edge of the number line. We're talking about limits at infinity. One of those huge ideas in calculus that asks a really simple but kind of profound question. What happens to a function when its input just gets bigger and bigger and bigger forever? Let's dive in.
So here's the game plan. We're going to start with what I call the dominance games, which is what happens with simple fractions. Then we'll zoom out to a full hierarchy of power that includes all kinds of functions. After that, we'll see how these exact same limits actually define the carrying capacity of our planet. And to wrap it all up, we'll uncover the secret origin story of the famous number e. Okay, so what really happens out there at the very edge of everything? Is it just total chaos? Does everything just explode and get bigger forever? Or do things start to calm down, to settle, to approach one specific, predictable value? That's the big question we're going to answer today. Let's kick things off with rational functions, which is just a fancy way of saying a polynomial divided by another polynomial. And the best way to think about their limits at infinity is to imagine a struggle for dominance, a real battle for control between the function on top and the function on the bottom. And the cool thing about this battle, there are only three ways it can end. First, if the numerator's highest power, its degree, is bigger, we call that top-heavy. The top wins, and the whole function just shoots off to positive or negative infinity. Case 2, if the denominator's degree is bigger, it's bottom-heavy. The bottom wins, and it pulls the whole thing right down to a limit of 0. And what if their degrees are exactly the same? Well, then it's a perfect tie, a stalemate. The limit is just the ratio of their leading coefficients. So if you have, say, 2x squared over 3x squared, boom, the limit is just 2 over 3. Okay, so those shortcuts are awesome, but you've got to know the formal method, right? The one that always works. So first, you're going to look at the denominator and find the biggest power of x. In something like 2x squared plus 1 over 3x squared minus x, that would be x squared. Then you divide every single term in the whole fraction by that power. This leaves you with 2 plus 1 over x squared over 3 minus 1 over x. And here's the magic trick, the most important part. Any term that looks like a number over x to some power, that thing is going to 0 as x gets huge. So 1 over x squared and 1 over x both become 0. And what are you left with? Just 2 over 3. Simple as that. All right, so we've got the rules for polynomials down. We know how they fight. But what happens when we throw some new challengers into the ring? What if it's not just an x squared fighting an x cubed anymore? What happens when a total heavyweight, like an exponential function, say e to the x, steps into the ring against a polynomial? Who wins then? Well, it turns out there is a very clear pecking order, a true hierarchy of power. Way down at the bottom, growing the slowest, you've got your logarithms. Then you have all the polynomials. But then, towering way above them, you have the exponentials. This is because exponentials grow by multiplying, like doubling, while polynomials just add. And here's the absolute key rule. An exponential function will always, and I mean always, eventually outgrow any polynomial, no matter how ridiculously big that polynomial's degree is. And even above that, you have monsters like factorials and x to the x. So, why should you care about this? Well, if you've ever used a computer, this hierarchy is like the backbone of everything. If an algorithm runs in polynomial time, we consider it efficient. That's why your app feels snappy and smooth. But if its runtime is exponential, we call that intractable. The time it takes just explodes for big problems. That's when your app just freezes, and you get that spinning wheel of death trying to handle a big task. This isn't just theory. It's literally the difference between an app that works and one that's totally useless. Okay, so let's shift gears now. We're going to take this idea from the digital world and apply it to the natural world. Because it turns out that limits at infinity aren't just for code. They're absolutely essential for modeling how populations grow and understanding the very balance of life on Earth. This idea that a population just doubles and doubles and doubles forever, it doesn't really work in the real world, right? Resources run out. That's where this thing, the logistic growth model, comes in. Now, I know it looks a little scary, but all it does is add a crucial limiting factor into the equation to model what really happens. So let's do what we do best and take the limit. What happens to this population, like way, way down the road as time goes to infinity? Well, look at that term e to the negative kt. Remember, a negative exponent just means you flip it to the denominator, so it's really 1 over e to the kt. As t gets gigantic, that whole thing shrinks down to basically 0, so the denominator just becomes 1 plus 0, which is 1, and the population, p of t, approaches k.
And that letter k, it has a really important name, the carrying capacity. Think of it like a ceiling, a horizontal asymptote for life itself. It represents the absolute maximum population that any given environment, with its limited food, water, and space, can actually support over the long haul. This is a limit at infinity that literally defines the boundaries of life. All right, for our last section, we're going to talk about one of the most famous, maybe even mysterious numbers in all of math. You probably know it from science or finance, but what you might not know is that the number e at its very heart is just the result of a limit at infinity. This is it. This is the secret formula, the very definition of e. It is the exact value that this expression, 1 plus 1 over n to the nth power, gets closer and closer and closer to as n just marches off toward infinity. And this whole idea actually came from a guy named Jacob Bernoulli, who was looking into, of all things, compound interest. Let's actually watch it happen. Imagine you have $1 and you get 100% interest. If you compound it just once a year, that's n equals 1, you get $2. Simple. But if you compound it monthly, n is 12, you get about $2.61. Okay, a bit more. Daily, 2.714. See what's happening? The jumps are getting smaller and smaller. It's zeroing in on a specific number. It's approaching a limit. And that final limit, the number you'd get if you could compound your interest not just daily or hourly, but continuously, an infinite number of times, that is the number e, which is about 2.71828. The absolute maximum return on that investment is defined by this incredible limit. So think about it, from how fast your phone works, to the balance of nature, to how money grows. These limits at infinity are everywhere, like a hidden blueprint for the universe. They tell us about the end game, the ultimate behavior of a system. So, what other parts of our world, or even our own lives, are really just heading towards some kind of ultimate limit?